Well, hello and welcome again to our journey through complex analysis, journey into complex analysis. And last time we finished looking at the Riemann sphere, and just do a little bit now in this next section on mappings. So the first thing, of course, to point out is that complex functions are four-dimensional. You can't visualize them because you need two axes to represent the variable z, if you've got w is f of z, and you need two variables or two axes to represent the variables u and v, for w is u plus iv, and that means you need four mutually perpendicular axes, and so you can't draw these. So you can't see what complex functions look like, but you can see what they do. And that's what this little section is about. And so one way of visualizing a complex function f is to regard it as a mapping of the complex plane onto itself. That is, we start out in what I call the z-plane over here, and we take some shape in here and we see what the function does to this, and the image of it will be over here in the w-plane. So firstly, if we take a complex number z and simply add a complex number a, then we can think of this as a translation by a vector a, thinking of this complex number as a vector. So we think of this really just as a translation. It moves the complex number z to z plus a. On the other hand, if we've got f of z as, say, wz or omega z, where omega is r e to the I theta, then what this will do is it will multiply the modulus of z by r, so that will give us a dilation, a stretching, and it will add theta onto the argument of z, and that'll give us a rotation anti-clockwise about the origin through an angle of theta. So this mapping, multiplying a complex number omega by the variable z, can be viewed as rotating z anti-clockwise about the origin through an angle of theta, while simultaneously dilating it by a factor of r. So just a little example here, we can do this. It says find geometrically the image of the line y is x minus 3 under the mapping w is I z plus 2. You can do it algebraically very easily. You just put z equals x plus iy, w is u plus iv, and you use this equation to eliminate the x's and y's, and you'll get the nice formula relating u and v. But it says here to do it geometrically. So I'm going to, there's our first line. This is the line y equals x minus 3 in the z-plane. And we want to see what happens in the w-plane. Well, firstly, if we look at what this is doing, it's multiplying each complex number, each point on this line by I, and that will simply rotate it, and then we've got a translation by 2 in the positive real direction. So that means if I started out with a line, it's going to map to a line of some sort. So I have a look at what it does to various points. So if I take, say, the number minus 3, when I multiply this by I, then this is going to, well, this is the point minus 3 on the imaginary axis. So multiplying by I rotates this through 90 degrees up to here, because I can write I as e to the I pi on 2. So modulus 1 and the argument's pi on 2. So it won't dilate it, it'll just rotate it for this part of it. So that point gets mapped to there, and then I'm going to translate by 2 units in the positive real direction for the plus 2 here, and that's going to send me across to the point 5, and so that point minus 3 gets mapped to 5 over here. Now the point, if I take, say, the point 3, then that gets rotated across to here. That'll end up as 3i when I multiply by I, and then I'm going to add 2. So this point gets mapped to the point 3i plus 2. Now if you look at these two, we said that this function is going to map a line to a line, and I look at the gradient of this little interval here from between these 2 points, and I see that it's minus 1. And so this then is obviously going to be the line u plus v equals 5. And that'll give me the other 5 up here on the imaginary axis. So that's thinking about it geometrically. You can do it algebraically as well. Another little example, slightly different this time. This is doing quite different things. This has got squares in it, so this is not going to be of the same sort we've been discussing. So f of z is z squared plus z to the minus 2, 1 over z squared. And we want to find the image of the unit circle. And now the unit circle, of course, I can write as z equals e to the I theta, where theta goes from minus pi less or equal to theta less or equal to pi. So I can simply go around the unit circle, or 0 to 2 pi if you like. So we can go around the unit circle, and when I plug that into my formula, so when I plug in e to the I theta, I get e to the I theta squared, that's e to the 2 I theta plus e to the minus 2 I theta, and of course you recognise that that's just twice the cosine of 2 theta, which by the way of course is real. And so this maps here's our unit circle here in the z plane, and it's mapping it to something on the real axis back over here in the w plane. And now as theta varies between minus pi to pi, this is 2 cos 2 theta, and so this is going to go from minus 2 up to 2. From minus 2 up to 2. Now in fact you can enjoy what's happening here a little more. If you start off at this point here, say at 1, that means theta is 0, and at that point f of 1 is going to be equal to 2. If theta is 0, we'll end up at 2. As I move around the circle up to here, up to pi on 2, over here the image is moving across to minus 2. So as you move around there, the w values are moving across to there. When you move down further to there, it moves back again. And if you move down to here, it moves back again. And back up to here, it moves back to home again. So as you go around this unit circle in the z plane, you're going back and forth in the w plane under this mapping. And notice that this is quite different. This is not mapping lines and circles to lines and circles. This is mapping a circle, in fact, to an interval. So this is quite a different kind of mapping to the ones we've been looking at. Very important kind of transformation are the so-called Merbius transformations, which I'll say a little bit about. And you can find plenty of information about this on the web and have a play with these. So a transformation f of z or w is az plus b over cz plus d, with a, b, c, d complex numbers. And also we insist that ad minus bc not be 0. I'll leave you to check that if ad minus bc is 0, then you can simplify this expression, and it turns out just to give you f is a over c, and that's a constant, and so we don't want this to be constant, so that's the reason why we exclude this case here. You might, of course, I hope, see that this is looking very much like a determinant of a matrix, and there is a connection between these Merbius transformations and matrices. This will tell us the corresponding matrix, in fact, doesn't, so it has an inverse. Anyway, this sort of transformation, it's linear over linear, with this particular extra property. This is known as a bilinear or Merbius transformation. It's called bilinear because you can rearrange, put this to be w, you can rearrange this to get this expression, and that's linear in both w and z. Now the mapping is invertible, which is very nice, so you can rearrange this and make z the subject and get the inverse. So notice then that if c is 0, so going back to here, if c is 0, then this is just linear, and that means the point at infinity, if you plug in z as at the point at infinity into a linear expression, then you get the point at infinity. So this, if c is 0, f maps the point at infinity to the point at infinity. If c is not 0, then if you map this across, if you take z as minus d over c, this is just a straight line, then this maps the point at infinity. If you put z equals minus d over c into this, then you get w is the point at infinity. And conversely, if you put the point at infinity into the inverse, then you get w is a over c. So that's just an interesting observation there. Now it can be shown fairly easily, in fact, that any line or circle in the complex plane has this form. It can be written in the form a zz bar plus b bar z plus bz bar plus c equals 0, any line or circle, with AC being real and AC less than the absolute value of b, or the modulus of b squared. If a is 0, then this disappears, you just get lines. And so also note that this equation above, our Merbius transformation, it maintains its form under the mapping z equals w minus b under translation. If you do a dilation, z equals w over a, or if you do z as 1 over w, that's an inversion, then the equation maintains the same shape, and hence all of these mappings take lines and circles to lines and circles. Because if you take a line or a circle and you translate, dilate, or take an inversion, then it stays as a line or circle. So the point being, these Merbius transformations map lines and circles to lines and circles. And of course you can think of a line as a circle with infinite radius. If c is not 0, then we can divide and we can rewrite the bilinear map as in this form, and then we can simply, so I'm just dividing everything by c firstly, and then I can split this into alpha plus this expression, so I get a constant on the top and the z on the bottom. And this again is simply, it's a dilation, sorry, it is a translation, plus it's got an inverse, and there's also dilations. If c is naught, then we simply have a dilation and translation. And so again, the conclusion of this is that the Merbius functions, Merbius transformations, map lines and circles to lines and circles. So just as a little algebraic example of playing with one of these, we want to find the image of x plus y equals 2 under this mapping w is 1 on z minus 1. So this is a very simple Merbius transformation. So here's what we do. Well, here's our mapping. W is 1 over z minus 1, and z is not 1. I can rearrange this. Now, I could, at this stage, put z as x plus iy, w is u plus iv, and equate real and imaginary parts, and that would give us a formula for u in terms of x and y and v in terms of x and y, but it's algebraically then difficult to get rid of the x and y using this to try and find the connection between u and v. So what we do is we try and make z the subject of this rather than w. So just rearranging, I get z minus 1 is 1 over w. Here again w can't be 0, which is important. And now I'm going to put z as x plus iy, w as u plus iv. And when I do that, when I substitute that into here, I just get this expression here. Now 1 over w, of course, is 1 over u plus iv, and I can multiply top and bottom by the conjugate, and then that'll realise the denominator and give me this expression. This then enables me to separate off equating real and imaginary parts. I get x is this expression and y is that expression. And I can just substitute these directly up into the line x plus y equals 2, and I get this equation here, which looks a bit of a mess until I clear denominators, and then you can see a lot more going on. When you clear the denominator, you simply end up with a u minus v. You take 1 from both sides, you get u squared plus v squared is u minus v, and I can bring these terms onto this side and complete the square. And here, of course, we immediately see that this is a circle, centre a half, minus a half, radius 1 on root 2. So let's just draw a picture to see what this is doing then. So we started off with the line x plus y equals 2 in the z-plane, and it maps to a circle, centre a half minus a half, which is here, and radius 1 on root 2. So it will be a circle like this, but you may recall that we said w is not allowed to be 0, so this point is excluded. And this is what it looks like in the w plane. And if we just enjoy the geometry of what's happening here, this line, this circle of infinite radius is being mapped into a circle, and the point at infinity is being mapped into 0. So if we take the point at infinity in the complex plane here, we go along the line this way or that way, doesn't matter, because you get the point at infinity either way, then that point is being mapped to the origin. By the way, you can check if you take a point in the middle here, then that one gets mapped diametrically opposite this missing origin here. And so that's what's happening. The line is being twisted around and turned back into a circle with the origin removed. Little, not very difficult, but little challenge problem if you want to play with these ideas a little bit more. So see if you can show that this is the principal argument of 1 plus e to the I phi, where phi is between minus pi and pi. If that's show that that is equal to 1/2 of phi. So if we take a phi, take e to the I phi, 1 plus e to the I phi, and take its argument, then the principal argument is a half the angle we started with. And hence use that to show that the image of mod z equals 1 under this mapping, this is not a Merbius transformation, it's got squares in it, under this transformation show that this is in fact a cardioid. So you'll be looking at this in polar coordinates to see that it is in fact a cardioid. Well, need to do a little bit on some analysis here, and just to mention limits and continuity, and hopefully you've seen a little bit of this in courses in real analysis, and we simply copy across the same ideas that we've had in real analysis. So we're going to say that the limit as z goes to z naught of f of z is capital L if, given any real number epsilon, there is a delta such that if z minus z naught is less than delta, so if we take a number, if our z naught is within delta of z, then our f of z is within epsilon of the limit L. If you've done courses in real analysis, you'll see we're just copying exactly across the definition we have for limits back in functions of one real variable. We just replace the x with a z essentially here. So a little challenge problem here. Write out a careful proof that if you've got the limit as z goes to z naught of f of z is L, then that works if and only if the real part of the u of the real part of f goes to the real part of L as z goes to z naught, and the imaginary part of f goes to the imaginary part of L as z goes to z naught, where this f of z is u plus iv. Something which you might expect to be true, but nice to write out a careful proof of that. So we say that the function f of z is continuous at z naught, if and only if the limit as z goes to z0 of f of z, well, this assumes it exists and it equals f of z0. That is, given any real number epsilon, we can find a positive real number delta, such that if z is within delta of z0, then f of z is within epsilon of f of z0. In physical terms, what it means is that if you start out with points that are close together, that is within delta of each other over in the z-plane, if the function's continuous, then the images of these are close together in the w-plane. So here we have the w-plane. i.e., you tell me how close you want these to be, you give me epsilon, I have to be able to construct a delta that tells you how close these need to be, so that if the distance between these is less than delta, the difference between these is less than the given epsilon. Now, just as one quick example of how one does this, here's a simple example of this. So we want to show that the f of z is the real part of z is continuous everywhere. In particular, I'm going to show that f is continuous at some general point z0 is x0 plus I y0. So we just recite the mantra, given epsilon bigger than 0, put delta equal to, not sure yet, we'll always leave a little gap here for the moment, I'll fill that in a second. Then the definition says that if z and z0 are within delta of each other, now think about what that means. You can square both sides of this because everything's positive, and I can write down explicitly what this is. It's just I've got rid of the square root by squaring, so there's just x minus x0 squared plus y minus y0 squared is less than delta squared. So if that is true, then we want to show that f of z and f of z0 are within epsilon of each other. So I just simplify this. The real part of f of z is x. Real part of f of z0 is x0. So that's what this is. And now I need to get this into the story because I've got some control over this. And so I'm just going to say this equals this at the moment. This is equal to the square root of x minus x0 all squared. Add in something and use an inequality sign to get this into the story. And now, of course, that is less than delta. Now, what difference did I want this to be less than? I wanted it less than epsilon. At the moment, I've squeezed this less than delta. Haven't told you what delta is yet. Now I do. I'm going to put delta equal to epsilon. And then I'm going to go and fill in the gap here. And now I've satisfied the definition. So given epsilon bigger than 0, we choose our delta to be equal to epsilon. Then if z and z0 are within delta of each other, then f of z and f of z0 are within epsilon of each other. So we've satisfied the definition. Now in practice, all polynomials are continuous, as are all rational functions whenever they're defined. As a general rule of thumb, I always think all functions are continuous unless they've got a very good reason not to be. So for example, if I take f of z as say z squared minus 3 on z squared plus 1, then this is a rational function. It's continuous everywhere except when I'm going to divide by 0, and that's going to happen now at z is plus or minus I. So while polynomials are in our minds, I'm simply going to state, and we will prove it later in fact, the fundamental theorem of algebra, which you'll recall that says every complex polynomial of degree bigger than 0 has at least one root in the complex plane. And we will have a proof of that later on in the section, in a later section. And of course, once you've got at least one real root for a polynomial, then you can in theory factor out z minus that root from the polynomial. You then have a polynomial of degree 1 less, and you can repeat the argument. And so counting multiplicity, every polynomial of degree n has exactly n roots in the complex plane. And that's the end of this section.